haven't been here. I should be back tomorrow. Things keep surprising me. So what we're going to do today is we're going to take notes on 7.2 and 7.3. Now, we've already focused on a lot of the graphing in 7.2. So notice right here, at the top of the slide, or top by the title, I guess it's not really at the top of the slide, you see that I say that you're going to want to look at your notes. So we're going to talk a little bit about graphing a certain exponential function here, and that's going to help us graph log functions also. And if you have to, you need to look back at your notes to recall how we did that. So first of all, the exponential function we're going to work on graphing today is an exponential function that uses a base of e. So e is a number, not just a letter. You can see there's two places on your calculator that you can find this. One is above the division sign. You just see the letter E. And then one is near the number 4. There's a button that says ln. And above that you see e to the power of x. So most of the time I use that one because that already gives me any button I would need to raise e to a power. So you can either just press E and enter, or e to the power of 1 and enter, to give you an idea of what this number is worth. So you should see on your calculator that it's worth about 2.718281828. And it keeps going, and though it might look like it repeats, it is irrational, which means it's a never-ending, non-repeating decimal, similar to like the number pi. Okay. So that's about it for that. They call this the natural number. Okay. And then we'll come back later to why it's connected to this button. That ln actually stands for natural logarithm, so you can see it's probably related to the natural number. Now, at any time in the video, if you need it to be paused, please just raise your hand and ask. The substitute can do that, and then you can watch the rest. All right. So the natural number comes about through a process that we're going to look at later. But a place that it's used is when you're talking about earning money from interest, specifically if the interest is compounded. So if it's compounded, what that means is that, let's see, if you get an annual interest rate of 4%, which would be a lot at a bank, that would mean that the bank would let you put money in for a year, and then there would be a date, one single date at the year, that the bank looks at all the money you have in there, and they give you 4% of that money, and there's your interest. Okay? But that is considered very simple interest. Compounded interest takes the percentage and divides it up. So let me give myself a little bit of an easier number. Let's say that your interest rate was 12% a year, and it was compounded monthly. Okay? So what the bank would do is they would say, well, we're giving them 12%, but we're not going to give them all to them at one time. We're going to give it throughout the year. We're going to give percentages monthly. So what they do is take the 12% and divide it by 12, because there's 12 months in a year, which means you'd get like 1% each month. And so instead of looking at your money one time a year, what they would do is look at your money after 1 month, give you a percent to add on to that. Then I look at your money again after the second month and give you a percent to add on to that. Now, this method is a little bit better because instead of waiting till the end, meaning your money's not growing unless you're putting it in there, your money's growing a little bit, even though it's less than the total percentage. It's growing a little bit each time that it's looked at. So the best case scenario would be this case where they say they're going to compound it continuously. So you'd think like, well, it's just going to keep going up. Excuse me, sorry. You think, well, it's just going to keep going up, so how do you represent compounding continuously? But if you actually look at what happens, it starts to increase as you compound it more and more and more, but then all of a sudden it levels off, and it levels off at that natural number, that e. So you can see the formula here uses a equals p times e to the power of r times t. So A is the amount. This is like the ones we saw before break, if you have to refer to those notes afterwards. P is the principal or beginning amount. E is the natural number, so that's already a number itself. R is the rate, so you're going to use that annual interest rate, and T is for how many years that you have it in there. So for number 1, it says find the compound interest on a principal of $10,000 at 8% interest. So the amount we're going to have here on $10,000, our percentage is 8%. And for part A, it says we're just going to keep it in for a year, times 1. And then we can put this whole thing into the calculator, which is why I said I like using the button that has E in a place for the power. So I'm going to do 10,000 times E. And then in the power, I'm going to make sure that I include 0.08 times 1 all in the power. And I get 10,832.87. The reason I'm going to round it to the hundredths is because we're talking about money. So $10,832.87. Now for part B, it's the same problem, but this time we're going to keep it in for 10 years. So let's look at what effect that has on it. So I have my $10,000. I have my rate of 8%, but now times 10 different years. I'm going to go ahead and enter that into the calculator. And this gives me a new amount of $22,255.41. So if I keep my money in there for 10 years without touching it, I would get a good return on my investment. Okay, but just so that you guys know, 8% interest in an account is a really good return rate for a bank, even though you think it might sound small. All right, the next thing we're going to talk about is graphing these functions. So you're going to think about this just like you would think about a normal exponential function. Remember that number E is just like having a base of 2.71828, etc. So it's basically exponential growth, which means I kind of expect it to go like this. And remember, we expect all of our graphs to have this asymptote and this point at 0, 1 for every parent graph. And this is a parent graph. It just has a kind of weird base since we're using the number E. So when I still plug in 0, I'll get 1. I still have this asymptote at y equals 0. And I know which way I expect the curve to go. Now I just need a couple other points. So when I plug in 1, I would get 2.7 something. And then I could plug in e to the negative 1. Now, if you're not sure what that would be, because it's hard to picture this as a reciprocal, you can plug it in one time, and you'll see it's like 0.36 something. So something like that. And then we get the curve that we expected. So this would be the parent graph for anything that I graph that's exponential that uses a base of e. So we'll see in the next problem, we're going to graph negative 2 e to the x plus 1 plus 3. Now remember, that means I want to take this basic graph. It had an asymptote at y equals 0, had a point at 0, 1, a point at 1 comma e, or 1 comma 2.718, and another point at negative 1 comma 1 over e, or negative 1 comma 0.3679. Okay? All right, so I have some reference points as far as that's what I would start with. So that's my basic graph, and then what I have to do is take into account the transformations. So remember, all the horizontal transformations are going to be up in the exponent. So right now, since it's just plus 1, that means we're going to go left 1. And then we have a few vertical ones. We have the negative, the 2, and the plus 3. So the negative is going to be a vertical reflection. The 2 is going to be a vertical stretch. All those distances times 2. And then the 3 is going to make the function go up 3. Now, in the videos you watched before break, we talked about graphing these and that the stretches and compressions get a little tricky because this time everything does not stretch or compress from the vertex. Actually, if you can stretch or compress from the asymptote, you will do that. But then sometimes either the vertical or the horizontal doesn't work that way. Then you should use the vertex point. So the first thing we're going to do is we're going to move everything to the left one. Okay. So what I'm going to do is two things that kind of help me. I'm going to use that parent function that I graphed, and I'm going to go through all the steps up here on the graph. I'm also going to keep track of the points that we have and then change them as we go so I know where my points should end up. So we have 1, 2.718, 0, 1, and negative 1.3679. Okay. All right, so with a shift of left 1, that's a horizontal movement, which means when I look at my coordinates, I expect it to change the x coordinate. And what I expect it to do is I expect it to move the entire graph left 1. So instead of 0, 1, I have negative 1, 1. Okay. So it's changing basically these x coordinates over 1. So this one's going to become, they're all going to change by 1. It's going to be at 0, be at negative 1, and this is going to be at negative 2. Okay. So at 0, I'll have my 2.718. At negative 2, I'll have my 0.3. I still have my asymptote in the same place right now. So right now, that's my curve. And I moved everything left 1. All right, now all the rest of these changes are vertical. So I shouldn't see any change in the x coordinate. It should be done now. Okay? But definitely the y coordinate is going to change as I do my vertical changes. Now the first change I'm going to do is a vertical reflection. Remember, that just moves everything below the x-axis instead of above the x-axis. So what that's going to do is put a negative on each of those. So each point is going to move so that it's below the x-axis instead of above. So you can see the vertical reflection of the graph. Now, a vertical stretch by a factor of 2. Think about where the asymptote is, and can you measure something vertically from the asymptote? And I can. Like, I can look at this point right here and say, okay, it's 1 unit away from the asymptote. Since you can measure from the asymptote, then your stretching of distances is going to be the distance from the asymptote, not from the vertex. So what that means is, right now this point is at negative 1, negative 1. So the distance from the asymptote to the point is 1. But I'm multiplying it by 2, so I want to change that distance so that it's 2, which would put my point here. So notice it's kind of multiplying the y coordinate by 2. So instead of this being negative 1, negative 1, it's now negative 1, negative 2. So in this top point, remember the x coordinate's not going to change, but the y coordinate is. So when e gets multiplied by 2, or negative 2.718 gets multiplied by 2, I get negative 5.436. So that would stretch that point to there. And then the negative 0.3679, that's how far it is from the asymptote, is also going to get multiplied by 2, which is going to be negative 0.7358. So you can see everything was stretched vertically, okay, away from the asymptote a little bit. Then the last thing we're going to do is move everything up 3. So it's going to be our final graph. I'm going to put it again in blue, like I did our purple, I guess, like I did our parent function. So if we move everything up 3, this is the one shift that affects the asymptote. So the asymptote is now here at y equals 3. And then all the points move up 3. So again, as far as the y coordinate goes, that would be like adding 3 to each of the y coordinates. So instead of negative 5.436, if I add 3 to that, this is going to be negative 2.436. Instead of negative 2, if I add 3 to that, it's going to give me positive 1. And instead of negative 0.7358, if I add 3 to that, that's going to give me 2.2642. So I have my points there listed if I need them, if that helps me graph them. And I'm going to mark them on here and draw my final version of the graph. So this is kind of what I would get. I have points if I need to list one. This one is kind of my vertex point. I have the equation of my asymptote, y equals 3. I have all the transformations listed. All right. So just a reminder of how exponential functions worked, and the only thing different about this one is we had kind of more difficult numbers because we were using a base that was an irrational number. Now, I mentioned the word logarithm once today already, and I know you guys may have accidentally seen a video on logarithms, and some of you might know what they are. So our goal is to talk about them today. So first, to understand a logarithm, you just have to understand exponents. Okay? So basically, if you have an exponential function like y equals b to the x, you can rewrite that function as a logarithm. So logarithms are completely related to exponential functions. So you write the word log, short for logarithm, and a logarithm has a base like an exponential function. So notice the base in the function ends up there. But notice I've kind of switched sides with the y and the x. Basically, a logarithm is a question. Okay? For example, an exponential function would say 2 to the third power might equal 8. Okay, because I know 2 to the third power is 8. In logarithmic speaking, this means a logarithm base 2 of 8 is equal to 3. Notice that the answer when you calculate a logarithm is the exponent. So basically, a logarithm is posing a question about what exponent should you put on this base to obtain this answer. So like when we look right here, log base 3 of 9, remember that's asking you what exponent should you put on 3 so that the outcome is 9. Okay? And the answer to that would be 2, because 3 to the second power would be 9. Okay? And for part B, where it says log base 5 of 125, that's saying 5 to what power is going to result in 125. So my answer to that is that that is worth 3. Okay? So when I see a logarithm, I'm reading it as a logarithm. I understand what the base is, and notice how I've said everything. But really in my head, I'm thinking about exponents to come up with the answer. A common logarithm function is just based on what we base our number system on, which is 10. So basically, the reason this is up here is I wanted to remind you guys that if we wanted to write a log with base 10, we don't normally write base 10. Sometimes you'll see that like that. But a lot of times you'll just see, notice, no base at all. That doesn't mean it's missing a base, because a logarithm doesn't make sense without a base. How do you know which exponent gets you your answer if you don't know what base you're using? You wouldn't. So basically, if you see no base, you really need to think about it as base 10. Okay? And they call that the common logarithmic function. Okay? One other example of like how to transform things. Let's say I had log base 1/2 of x equals 16. no, sorry, I want 16. I want -3. And let's say it was really hard to rack my brain around what x should be in that form. Remember that I could rewrite that in exponential form, and that would be a base of 1/2 to a power of -3 equals whatever's inside the logarithm here, which this time just happens to be x. And then that would actually be a solvable equation. You should be able to calculate 1/2 to the -3 power. All right, so a couple calculations on what to do if you can't come up with them off the top of your head. So first thing I do is just think if I know it. 1/2 to what power gives me 2? That would give me the answer to this problem. If I don't know it, what I need to do is turn it into a little equation that I can solve, putting x where I'm looking for my answer, and then using other things I know. So one other thing I know in this case is to rewrite problems with the same base. So maybe instead of 1/2, I write this as 2 to the -1 power. And I have 2 on the right side, which is like 2 to the first power. Then I know I could set these exponents equal to each other. And I get x is equal to -1, which really means log base 1/2 of 2 is -1 because 1/2 to the -1 power equals 2. Okay. All right, so same thing with part B. If I don't know off the top of my head 4 to what power equals 32, then I'm going to set it up as 4 to the x equals 32. I'm going to rewrite both problems with the same base. So in this case, I would use 2. I will set then the exponents equal to each other. And I would get that x is 5/2. Or in other words, the answer is 5/2. And that means that if I take 4 and raise it to the 5/2 power, I would get 32. Remember, you guys can ask to pause the video at any time. The last one, do I know what power to put on 64 to get 1/32? And if I don't, then I'm going to rewrite using x to kind of symbolize where the answer I'm looking for should be. So 64 is like 2 to the 6th power. And 32 is like 2 to the 5th power. But it's in a fraction, so I'll use that negative exponent. I'll set them equal. So I have x equals -5/6. In other words, my answer is -5/6, or -5/6 is the exponent I would place on 64 to get 1/32 as an answer. The next thing we're going to do is we're going to graph logarithms. So what we're going to do is graph what we would consider a parent function, and then we'll do some transformations of that. Now, before we do that, I want to go back here and just make a couple of notes about calculating some other logarithms. Okay, log base 5 of 1. 5 to what power would equal 1? That would be 0. And it actually wouldn't matter what you changed the base to. Like log base 12 of 1, 12 to what power equals 1 would still be 0. So one thing I want to point out is that the log of 1, no matter what the base is always going to be 0. The other thing I wanted to point out is taking the log of 0 or a negative. Now remember, you're asking yourself, 8 to what power equals 0? Well, no exponent has the property that it turns things into 0. So this has no solution. And same with the negative. 8 to the first power is 8. There's no power I can put on 8 to all of a sudden make the base negative. So that also has no solution. And our base is always going to be a number between 0 and 1, or else bigger than 1. So all positive stuff not equal to 0 and not equal to 1. So these situations, you can't really take the log of 0 or a negative. And that's important when we go to graph, because we kind of know that we can't plug in for x 0 and we can't plug in a negative. So there actually exists a vertical asymptote in logarithmic graphs at x equals 0. At least in the parent graphs, and then obviously once you shift it, it could change. And then to get some points for this graph, I'm going to pick things that are easy to calculate. So first thing that's easy to calculate is to plug in 1, because we just said log base anything of 1 is going to equal 0. So there's the point 1, 0 on this graph. Then I want to pick good things that I want to take the log of, and note that I'm using base 3. So for me, good numbers to take the log of, good things to plug in would be 3 itself, because 3 to what power equals 3? That would be the first power. And then the other thing I would choose is 1/3, because 3 to what power will turn it into 1/3, and that's -1 because it'll just flip it over. So every time I graph one of these, I start with the parent function, and I'm just going to use the number itself and its reciprocal to get those points that are like 3, 1, and 1/3, -1. And that is our graph of our log function. It's growing very slowly, okay, and follows the asymptote. So then, just like with exponential functions, we can graph this with transformations. Okay? So just a reminder that our parent function started out with a vertical asymptote here, and it went like this with 3 points, and the 3 points that we used were 1, 0, 1/3, -1, and 3, +1. And what we're going to do to that graph to get this new graph is include these transformations. So all your horizontal stuff is going to happen with whatever is kind of within the logarithmic function. So there we see it's being multiplied by a 2. So remember that that's actually a horizontal compression, where all those horizontal distances are getting cut in half. Now remember, distances here, if we can measure from the asymptote, we will, and if we can't, then we'll use the vertex. Then vertically, there is a vertical reflection because of the negative. And then we're going to move our graph up 1. So I'm going to go ahead and put in, let's see, I'm going to do the first transformation. So a horizontal compression of a half. Remember what I told you. That means I'm taking the current distance they are from the asymptote, since I can use the asymptote, and that's getting multiplied by a half. So currently that point was 1 unit away. 1 times a half is going to make it half a unit away, since the asymptote's at 0. Okay? Instead of this point being at 1, 0, this point's going to be at 1/2, 0. So it's not changing the location of the asymptote because we're stretching towards and away from that. But this point that was at 1, 0 is now at 1/2, 0. This point right here was already only 1/3 of a unit away from the asymptote. 1/3 times 1/2 is going to make it 1/6 of a unit away. So we're going to have 1/6, -1. Really, really close. And then this last point here was 1 unit away, and that times, 3 units away, because we're looking horizontally, and that times a half is going to make it 3/2 units away, or 1.5. So instead of 3, 1, it's going to be 1.5, 1. So there's our horizontal compression. A vertical reflection flips points over. Oh, this is why. Sorry. 1/2, 0 should be right here. Sorry, you guys. Fix that point for 1/2, 0. And then the same thing for 1.5, 1. I was graphing everything one above where it should have been, so I'm sorry. Fix those points. The points were listed right up there. I just didn't graph them correctly. So now we're going to vertically reflect everything. That means our vertex is going to stay the same and our asymptote is going to stay the same. But like this point here is going to flip below the axis, and this one here is going to go above. This one's going to stay the same. So our graph is going to go like this. Now remember what that did is that changed the y coordinates to their opposites. So this is like 1/6, +1 now, and 1.5, -1. We've done this and this. The last thing we have to do is move everything up 1. Now notice that contrary to the exponential graph, moving up and down does not shift the asymptote. Only moving left and right would. So the asymptote stays at x = 0. And moving everything up 1 is going to change all of those y coordinates by 1. So these x coordinates are going to stay. If I could write them properly. But everything's going to move up 1. So this is going to be at 2, at 1, and at 0. Okay? So 1/6, 2, half, 1, and 1.5, 0. So there's our final graph. So you have to learn what these logarithmic parent functions look like and how to get those points I did at the beginning of this graph when I did part A. We'll do one more of these. All right, so same thing. This is going to be a parent function, so it's still going to have the fact that we can't plug in 0 or a negative. So this asymptote kind of divides our graph into the usable and non-usable portion. Now, again, when I create this parent function, I want the easiest things possible to plug in using log base 1/2. So for me, I believe that that's using 1, and then it's using the number that's the same as the base and the number that's the reciprocal of the base. So here I've plugged in 1, I've plugged in the same number as the base, and the number that's the reciprocal of the base. And this gives me results of 0, 1, and negative 1. And those are 3 points that I can draw my curve from. So 1, 0, 1/2, 1, 2, negative 1. So notice it's still a similar curve, kind of going the opposite way, like growth and decay relationship. So this is a parent function. We're going to use this parent function to graph part B, which has some transformations of this. Okay, so a little reminder that we start with our asymptote at x equals 0, and that this time we had 3 points kind of oriented like this. And those 3 points were 1/2, 1, 1, 0, and 2, negative 1. So here, there's 2 transformations happening. Here's our horizontal transformation, which is to move the graph left 2. And then here is our vertical transformation, which is a vertical stretch times 3. Now, in this case, to stretch it vertically, since the asymptote is here, I cannot measure vertically from this asymptote. It doesn't make sense. So this time when I'm stretching, I'm going to be stretching from the vertex point, and I'll show you guys what that looks like. So the first thing I'm going to do is move everything left 2. Remember what that's going to do to my points. This is a horizontal change. So 1/2 shifted left 2 is like subtracting 2. So it's going to be negative 1.5, negative 1, 0, and 0, negative 1. Okay. So negative 1.5, 1, negative 1, 0, and 0, negative 1. So that doesn't make sense with an asymptote still at 0, and that's because your asymptote has been shifted also. So if it's been shifted to the left 2, it's now going to be here at x equals negative 2 instead of at x equals 0. Sorry. Then we're going to vertically stretch by 3. So our x coordinates aren't going to change. Our y coordinates are going to change by a vertical distance. But this time when we're stretching, we can't measure a vertical distance from this asymptote. We can only measure horizontally. So we're going to use the vertex as our reference point. So it's going to stay where it is. Okay, so this point is going to stay. And then notice that, like if I pick this point, it's 1 unit away from it vertically. We're going to stretch that by 3. So 1 times 3, we want it to now be 3 units away from it. So it's going to end up 1, 2, 3 units away from that point, so up there. And the same with this one. It's 1 unit away. It needs to be 3 units away, but in the other direction. So we're going to get this stretched version of the curve. And the way those points will change is they basically got multiplied by 3, so this one is now at negative 3. This one is at positive 3. So there's my points. I have my asymptote. I have my graph. So you want to know the shape of the log graphs and how to transform them. So then work on the assignment that the substitute has for you.